All right, so we left off, we were solving trigonometric equations, right? And this was different than the test. Oh, you know what? I got another housekeeping thing. So I'm in the process of going through everybody's exams and correcting any kind of syntax errors. I'm probably a third of the way through because I just started this morning. So I'll have that done today. For you to know if there was an adjustment to your exam, you actually have to go into the My Math Lab grade book, and if you see an asterisk next to your score, then that means that I went in and adjusted your score. Okay. All right, so back to what we were doing with solving equations. So we were solving equations, and remember that we were looking for sister triangles, not just using the pure definition of our inverse trig functions like we did on the exam. So the next set of directions is slightly different. Here it says solve, give all exact solutions. We know that there is an infinite number of coterminal angles, right, that represents the same angle. What you're going to do when the directions are to give all exact solutions, well, exact tells us that we're in radian, but to get all the solutions, we need to account for every angle coterminal to the answer that we have. So anytime you see it say give all exact solutions, we're going to write the same thing. We're going to get our answer like normal, and then we're going to add, if we're in radian, 2 pi n, where n is an integer. So this little weird looking e means is an element of, and that bold-faced z is our shorthand for integers, just like we have bold-faced r for all real numbers, the bold-faced z is for integers. So what's happening when we write this expression, if n is an integer, and we take any integer and multiply it by 2 pi, we're going to be getting multiples of 2 pi. 2 pi, 4 pi, 6 pi, and that's what's giving us the coterminal angles. Now, if we were asked to give our answer in degrees, we would then write plus 360 degrees n, where n is an integer. So that's something that you're going to have to add in anytime those are the directions. Now, My Math Lab, they don't have you put in this n as an integer part. They just have you write the plus 2 pi n or plus 360 n. But when you submit your take-home quiz, I'd like n to be an integer in there, because if n is not an integer, you're not adding a whole 2 pi. If n is a fraction, we're only doing a partial trip around the circle, and that's not the same thing. That's not what we're trying to accomplish here. Okay. So let's solve. Cosecant squared of theta over 2 equals 2 secant. Well, right away, I notice a couple things. I see that I have not the trig functions that I'm most comfortable with, which include sine and cosine. I also notice that I have 2 different arguments. So I'd like to be able to get in terms of a single trig function and to have an argument of just theta. To get rid of that argument of theta over 2, we would use a half angle formula, but we don't have a half angle formula for cosecant. So what do you think we should do to deal with that?
I'm sorry, your sound cut out. I didn't hear what you just said.
Okay. So we have 2 different arguments, theta over 2 and theta. And anytime we're solving a trig equation, we like to get it in terms of the same trig function and the same argument. Well, to transform theta over 2 into theta, we need a half angle formula, but we don't have a half angle formula for cosecant. So what do you think we should do first?
Can we use the Pythagorean identities for cosecant?
What do you mean by that exactly?
Well, cosecant squared is cotangent squared plus 1.
Okay, that is true, but what does that do to help us? My
Well,
other
tan,
trig function is secant, and it doesn't help me get to a similar argument. So although that's a true statement, it does not move us into the direction that we need.
okay.
But good idea, and that's some of the things we have to do. I just have to try some ideas and see if it gets us somewhere, and if not, well, then we'll try something else. Well, what kind of trig functions do we have half angle formulas for? Sine, cosine, and tangent. So is there a way that we can transform that cosecant squared into sine, cosine, or tangent? Sure, this right-hand side would become 1 over sine squared of theta over 2. Now I'm going to write theta over 2 squared because I'm just switching my notation a little bit because my half angle formula contains a square root and I'm looking to square that square root. Since I'm turning my left-hand side into something where I can use a half angle formula, and the half angle formula actually has cosine in it, I'm going to switch my right-hand side into cosine. So this is going to become 2 over cosine. Plugging in our half angle formula for sine, this becomes 1 over the square root of 1 minus cosine theta over 2 squared. Any questions so far? On the left, our square and square root are going to cancel out, leaving us with 1 over 1 minus cosine over 2 equal to 2 over cosine. Now we have an equation that has a single trig function, and that single trig function has the same argument. So this is a very positive direction for us. Now we just need to figure out how to solve that equation. Any ideas? Like, algebraically, what type of equation do we see, and then how do we solve that type? We're solving for theta, and theta is located in the denominator. So what kind of equation is that algebraically when the variable we're solving for is located in the denominator? Starts with an R. How about rational? So we want to clear the fractions when we have a rational. This happens to be a special type of rational, a proportion, since we have one fraction equal to one fraction, so we can simply cross multiply. So 1 times cosine will be cosine. And then we're going to have 2 times 1 minus cosine over 2. These 2's are going to cancel for us. Cosine is 1 minus cosine. And now we want to solve for theta. It's linear, so let's get all our cosines together. We'll isolate that cosine. And then we'll use inverse cosine to find our theta. Theta is going to be cosine inverse of 1/2. We're looking where on the unit circle cosine is equal to 1/2. If cosine is positive, which quadrants are we going to have to be in?
Isn't it 1 or 4?
It's going to be 1 or 4. You got it. And 1/2, that's our short side of our 30, 60, 90 triangle. So short, long triangle. That's going to be a 60-degree reference angle in each of these. It's that exact answer, so I know I need to be in radian. So in quadrant 1, what's that radian measure? Pi over 3. And then in the fourth quadrant, that 60-degree reference angle gives us 5 pi over 3. But since it wants all solutions, once we get these, now we just have to write our plus 2 pi n, where n is an integer for each of these. And I promise on the next test, you'll definitely have ones where you need to give me all solutions like this. Questions at all?
On the test, is it important that we had the notation just like that?
So on the test, my math lab is going to want this.
Okay.
On your quiz, I'd like to see n as an integer as well.
Okay. Thank you.
Anybody else? Yeah, if you don't have this extra part here, then you're not giving all solutions. It's not giving all the coterminal angles. So we got to have that part. All right, next up is an application problem here. A coil of wire rotating in a magnetic field induces a voltage modeled by E equals 20 times sine of pi t over 4 minus pi over 2, where t is time in seconds. We want to find the smallest positive time to produce each voltage. Part A, E is equal to 0, and in part B, E is going to be equal to 10 square root of 3. So basically, we got two little problems to do here. I'm going to split the page. First, we have E equal to 0, so we're substituting 0 into our equation for E. I think I'm going to write this pi over 4 and then the t off to the side. I like that better. Minus pi over 2. And now we're just solving for t. In this equation, we have a single trig function, so we want to isolate that single trig function. What should we do first? Anybody? What should we do first? Well, I know I can't. Oh, go ahead.
Should we divide the 2, 0 from both sides?
Yeah, we're going to divide both sides by 20 to start. Now, I know there's a lot going on in the argument. However, we have isolated our sine function. So we are ready to take our inverse sine. Now, before we were just saying like theta equals sine inverse or whatever. Well, in this example, this whole huge thing is our argument. And when we write this, we end up with, instead of theta equals, we're going to get pi over 4t minus pi over 2 equals sine inverse of 0. Any questions on the rewrite there? Well, let's figure out where sine inverse is 0. What sine inverse of 0 is. So where on our unit circle does sine have a value of 0? It happens at 0 and pi. Now I know to be in radian because I got all those pi's over here in my argument. So it doesn't seem like it would make a lot of sense to have degree measure with that. So I know that I want to be in radian. It follows that pi over 4t minus pi over 2 equals 0, or pi over 4t minus pi over 2 equals pi. And then we're going to solve each equation for t. Starting with the first one, I'm going to add pi over 2 to both sides. And then we'll divide, so multiply by the reciprocal. We get t equals 2. And then solving our other equation for t, adding pi over 2 to both sides. It's going to give us a 3 pi over 2, and then dividing by pi over 4. What do we get there? 6. And the direction said find the smallest positive time to produce each voltage. So we don't want the 6. We want the 2, and don't forget your unit of second. Questions, anybody?
Could you stop for a second? I'm still writing down.
No problem.
Thank you.
So I'm actually going to stop the recording, and I'd like you guys to do the next one. So all you're doing is replacing the e in our equation with 10 square root of 3.
Okay.
And then solve. You're taking the exact same steps. The only thing that's going to be different is, actually identifying what angles on the unit circle produce our answer. So I'm going to pause everything, and why don't you guys try it. So I ended up getting 10/3 seconds. Anybody have any questions? You guys are super quiet today. I feel like the course picks up here in this,
Yeah, sorry, they're remodeling the place I'm living at, so it's really hard for me to be able to talk.
no, that's fine. You always talk, Amber, that's okay. But everybody else is being super quiet today. I just want to make sure because I feel like Trig, 103, if you took 103, it kind of peaked in the middle and then tapered off at the end, and Trig increases in difficulty as the course continues on. I just want to make sure that people are asking questions.
Where'd you get the 5 pi over 6 from?
I
The 7
added
pi over 6?
the pi over 2 to both sides, so pi over 3 plus pi over 2 gives us 5 pi over 6 because I got to get a common denominator. And I did the same thing over here. And you guys are all taking this class because eventually you're going to calculus, and I feel like what you need the most out of trigonometry is your ability to solve equations. That's what you're going to be doing all the time in calc. So it's just, I know it's weird to kind of ask questions over Zoom and stuff, but you got to do it. This is anybody questions before we move on to the next one? All right. So here's another application problem. This is the distance of a thrown object. You do not need to memorize this formula. When throwing an object, the distance achieved depends on its initial velocity, v sub 0, and the angle above the horizontal at which the object is thrown, theta. The distance d in feet that describes the range covered is given by d equals v sub 0 squared divided by 16 times sine of theta times cosine of theta. And v sub 0 is measured in feet per second. So you and your friend are throwing a baseball back and forth. You throw the ball with an initial velocity of 90 feet per second. At what angle of elevation theta to the nearest degree should you direct your throw so it can be easily caught by your friend located 170 feet away? So we're looking for theta in this equation here above. So that means we better have a number for d and v sub 0 to plug in so that we can solve for theta. Well, they tell us that our v sub 0 is 90 and our friend is located 170 feet away. So that's our d. And we're going to plug in and solve for theta. 170 equals 90 squared over 16 sine of theta cosine of theta. I guess we can start by squaring 90. We have two different trig functions, which is never our preference when solving an equation. We like to be able to get down to a single trig function. Now, I do know that sine and cosine are related using the Pythagorean identity, but those are all for sine squared and cosine squared. So to substitute it in for just like not a squared, like we'd have to substitute 1 minus sine, the square root of 1 minus sine squared in for cosine. And I don't really want to introduce a square root if I don't have to. Plus, I can't then combine those two sine functions. So I want to think of something else to do. If you take a look at your formula sheet, do you see any formulas? And chances are we're going to be looking on the right-hand side that that have sine times cosine. Or I guess, even on the left-hand side, do you have any formulas that have sine times cosine? I see two of them on there. I see my double angle formula for sine, right? It says 2 sine cosine. Here I have the sine cosine. I could probably get a 2 out of that fraction. Or we have our product to sum identity that tells us that when we have sine times cosine, that's 1/2 sine of a plus b plus sine of a minus b. So we can use either one of those equations to help us get down to a single trig function. Because a double angle formula gets us to sine of 2 theta, and the product to sum takes us to both sides. So either one is good. Do you guys have a preference?
Could we do the second one? I forget what it was.
Hey, I forgot too. What do you want? The product to sum?
I think it's product to sum.
Yeah,
Yeah.
sure. All right, so to do the product to sum, I want to get rid of this fraction first. So let's divide by this here. And I'm sure it does not go in nice, so we're just going to leave it as a fraction, whatever we get over here. Does anybody have an answer? I don't have it. Is that 136 over 405 once we simplify it? And now we'll use our product to sum identity. So this is going to be, I think I'm going to put it all over 2. I'm not going to put the 1/2 out in front. All right, so this is going to be sine of theta plus sine of theta minus theta all over 2. I'm going to do 2 separate things here. I'm going to combine those arguments, and I'm going to multiply both sides by 2 to get rid of this denominator here. It's going to give us 272 over 405 equals sine of 2 theta plus sine of 0. Well, what's sine of 0? That's on our unit circle. What's sine of 0? Zero's right here. What's our sine value? 0. So we're looking at just 272 over 405 equals sine of 2 theta. We have a single trig function isolated. Oh, we're ready to do our inverse trig function. Two theta is equal to sine inverse of 272 over 405. Now, usually when I'm just talking about stuff, I don't say, oh, turn that pi over 3 radian. I will say 45 degrees or 90 degrees or something like that. So we're going to want to be in degree mode here. So let's put this in our calculator. Sine inverse of 272 over 405. Gives us a 42.1911. Now, if it wasn't an application problem and it was just, find the solutions on the interval 0 to 2 pi, I'd need to find the sister triangle. And then because our argument was 2 theta, we'd actually need to go a second trip around the circle. But because it is an application problem, throwing something at an angle of, 417 degrees does not make sense. So we are not going to find those additional ones. I mean, you could and then rule them out because it didn't make sense for the context of the application. The last thing we need to do here is divide everything by 2 because we're solving for theta. We get theta to be equal to, I bet we're rounding to the nearest degree. It ends up being 21.1, but we'll just round it to 21 degrees. There we go. Questions at all? Anybody? Any questions at all in general on solving trig equations? Which again is probably, in the top 5 things for you to learn in this course is your ability to solve trig equations. All right, so that's the end of chapter 6. We're going to start chapter 7, where we're going to be talking about triangles that are not right triangles. So everything that we're going to do here, SOHCAHTOA does not apply unless somehow a right triangle pops up. But we got to learn how to deal with things that aren't right triangles. The first thing we're going to talk about is our congruence axioms for triangles. This is something you would have discussed like in a geometry course in high school or something. Just what relationships have to occur to be able to say that 2 triangles are congruent, which basically means that they're equal. We just don't use the word equal because it's not the same triangle. It's a different triangle, but it's the same size. So first up is our angle side angle congruence axiom. If 2 angles and the included side of one triangle are equal, respectively, to 2 angles and the included side of a second triangle, then those 2 triangles are congruent. We also have a side-side-side congruence axiom. If the 3 sides on 2 different triangles are equal, then those 2 triangles are going to be equal. And lastly, our side angle side. So if you have a side, two sides and the included angle of one triangle equal to two sides and the included angle of a second triangle, then those two triangles are congruent as well. I mean, great, we have our congruence axioms. I don't want to say we don't really need them, but not so much. We don't need them here. But it kind of just gives us our intro to oblique triangles. So as I mentioned, up until now, we've only been dealing with right triangles, but moving forward, we're going to be dealing with triangles that are not right. Every triangle has 3 sides and 3 angles. If any 3 of the 6 measurements of a triangle are known, providing at least one of the measures is a length. We can't do it if all we know are the 3 angles. Then the other 3 measures can be found. The process of finding these other measures is called solving the triangle. Any triangle that's not a right triangle is called an oblique triangle. And we know that word oblique from like rational functions. An oblique asymptote is one that's slanted. Well, a right triangle, the sides are always straight up. So I think the term oblique makes sense because oblique means on a diagonal. So these are ones where the sides are on a diagonal rather than just straight up and down. Please note that an oblique triangle is either going to have 3 acute angles or 2 acute angles and 1 obtuse angle. Also, as I mentioned, the relationships of SOHCAHTOA is restricted only to right triangles and is not going to be applicable to any of these oblique triangles. There are 4 possible cases for oblique triangles, like the information we could be given out of the 6 possible measurements. We could have 1 side and 2 angles, and that could either be arranged as side angle angle or angle side angle. We could have 2 sides and 1 angle not included between the 2 sides. That's SSA, side side angle. This case can lead to more than 1 triangle. We'll talk about that case next week. Case 3 is 2 sides and the angle included between the 2 sides is known. That's our side angle side. And then lastly, all 3 sides are known. We're going to learn 2 different laws, one called law of sines and one called law of cosines. Case 1 and 2 require the law of sines, while case 3 and 4 require law of cosines. But like I said, I don't remember them as the congruence axioms. I'm going to show you something else when we're given a problem to know whether we're going to apply law of sines or law of cosines. I want to point out that all of these, 3 out of these 4 cases are a congruence axiom, right? These 3 are congruence axioms. The only one that's not is case 2. And case 2 is typically the trouble case. As it's mentioned, it can lead to more than 1 triangle. So I do actually remember this because, when you're in 9th grade, it was super awesome when your teacher said a swear word. So I can remember in the 9th grade, Miss Van Wee saying ass is not a congruence axiom. So if we flip that backwards to ASS, that's not one that works. So I don't know, that might help you remember where the tricky case comes in. It's if you have a side, and an angle not included. All right, so I'm going to start by deriving the law of sines so we really understand where it's coming from. I'm going to start with an oblique triangle, such as the acute triangles shown below on the left, or we could have the obtuse triangle shown on the right. So it could be either one of these. This discussion applies to both triangles. I'm going to start by constructing a perpendicular from B, all right, our angle B there, to side AC. Or in the case where I have this obtuse triangle, I had to like extend side AB because I'm trying to make a right angle here. If I let H be the length of this perpendicular, aka the height of the triangle, right? Then C is the hypotenuse of the right triangle ADB. Well, since I have a right triangle there, SOHCAHTOA is going to apply. In the acute triangle, and I'm looking at this right triangle right here in the acute triangle, sine of angle A is going to be opposite over hypotenuse. So we get that sine of A is H over C. I can then solve that equation for H and end up with H being equal to C times sine of A. Well, now I'm going to look at the obtuse triangle. I dropped a perpendicular to get the height, and I've created this right triangle right here. Again, I'm going to do SOHCAHTOA using angle A, opposite over hypotenuse. So, oh shoot, sorry. I meant to look at the big triangle. Sorry. All right, sorry. I want to look at the big right triangle here. And I'm going to use angle C as my reference angle, but still doing SOHCAHTOA. So from angle C, if I want to do sine opposite over hypotenuse, I get sine of C equals H over A, and then I can solve that equation for H, and I get this right here. Well, our transitive property of equality, since H equals both of those two things, H equals C sine of A and H equals A sine of C, I can just set the two right-hand sides equal to each other using our transitive property of equality. So we get C sine of A equals A sine of C. I can divide both sides of this equation by sine of A sine of C. That's a legal math move. I'm going to get stuff that cancels, and we're going to be left with C over sine of C equals A over sine of A. Any questions so far? Well, I could do the same thing just by labeling the triangle differently from the other vertices and stuff. So we can also show that A over sine of A would be equal to B over sine of B, and B over sine of B equals C over sine of C. So I can just put like cram all this together, and we can conclude that A over sine of A, which is equal to B over sine of B, would also be equal to C over sine of C. And that is our law of cosines. You'll see that I have the law of cosines written two different ways. Sometimes we might have the side on the top, and other times we could put the angle on top. We get the same thing because if I go back up here to where like I divided, if I decided instead of dividing by sine of A sine of C, if I just divided by A and C and canceled, you see that we get sine of A over A equal to sine of C over C. So it doesn't matter which one's on top, you just have to be consistent. Either you're putting all your sides on top or you're putting all of your angles on top. You just have to be consistent. I kind of flip-flop back and forth between the two. Probably I put the signs on the bottom more times because, I don't know, visually I just like my denominator to look bigger than my numerator. No, you will not be tested on the derivation. I just like you guys to understand where it comes from. But you absolutely need to remember the law of sines. We're going to start by dealing with case 1 triangles. But like I said before, I can't remember all the cases and which one's which and what congruence axiom and all that stuff. So what I like to do instead is I know that I'm going to use the law of sines if I have a known pair. And what I mean by that is I have to have angle A and side A. And we know that those are going to be like crossed each other from the triangle. So I either have to have this angle and this side, or I need to have this angle be known and this side, or this angle be known and this side. So if I have a known pair, then it's a dead giveaway that we want to use law of sines. We are going to determine the remaining sides and angles of each triangle, rounding our answer to the nearest hundredth. The direction could also be solve the triangle, because that's what that means, just find the rest of the answers. Since I have angle C and side C, I know that law of sines is going to be applicable because there's my known pair. We need to find angle A, side A, and side C. What would you like to find first? I always like to start with the easy stuff. What would be the easiest thing to find?
Let's do angle A first.
Yeah, I would totally find angle A first. So how are you going to find that?
Add 74.08 degrees and 69.38 degrees, and then subtract that total from 180.
Perfect. So that'll leave us with 36.54 degrees. So there we didn't have to do much work at all to get angle A. We didn't have to use the law of cosines to get the third angle. That's the easy case. So on Tuesday, we'll deal with what's called the ambiguous case of law of sines. And in the ambiguous case, they only give you one of the angles. So you have to do way more work to get the angle measure. So if the angle measure was easy to get, it's going to be not the ambiguous case of law of sines. Okay, great. So now we have that. Now it's time to find our two sides. We're going to use our known pair. That's going to be 1/2 of our proportion. Right? It's going to be one of the fractions. C over sine of C. And now that's going to be equal to, we need to pick whichever side we want to find, put it on the top, and then sine of that corresponding angle in the denominator. So it doesn't matter. We're doing A's. Let's find side A. Oh, side A is unknown, goes in the numerator. We're going to have sine of 36.54 in the denominator, and now we need to solve for A. What should we do to solve for A?
Can you cross multiply?
Absolutely. And then the last thing we need to do to solve for A is just divide. So A is going to be equal to 45.38 sine of 36.54 divided by sine 74.08. You want to plug that whole thing into your calculator at once, and then we are going to round to the nearest hundredth. So anybody get an answer for A? How about 28.10? That's what I got. Did anybody else get that?
Yeah, I got that.
Yeah, I got it.
Right, and then our unit, don't forget that, meters. Now we're going to do the exact same thing to get our side B. Now I would go back and use the original pair given as the first half of this proportion because this side A is rounded and I don't really want to start my problem off with a rounded answer. I would most definitely start with 45.38 over sine of 74.08 and then do B over sine of 69.38 degrees. And we do the exact same thing. We'll cross multiply. And then we'll divide and we get B to be equal to 45.38 sine of 69.38 all over sine of 74.08. We'll plug that whole thing into our calculator at once and round to the nearest hundredth.
I got 44.17.
All right. Anybody else get that answer?
Same.
Great. And don't forget our units of meters. So there we go. Questions at all? Now, some of you may have noticed in this first step when I was solving, like right here, these first steps here, cross multiplying with, hold on. Okay. In this first step here, so cross multiplying was great, but really we didn't have to cross multiply in that first step. All we needed to do to isolate A and B was multiply both sides by what we had here in the denominator. Now that's not always the case. Sometimes the cross multiplication is necessary, especially when we get into the ambiguous case. So if you want to just cross multiply every time, fine, but we could have shortcutted it a little bit there just by multiplying both sides by what we had in the denominator. All right, well, why don't you guys try the next one? I'm just going to pause the video and give you guys, a few minutes to work on this. If you have any questions along the way, though, just holler for me. I ended up with angle C being 66.2 degrees, side B being 80.13 centimeters, and side C being 74.07 centimeters. Anybody get anything different? I typically double check my answers just with like a general geometry fact. Remember that small sides are across from small angles and big sides are across from big angles. So I kind of look at my angles and look at them in increasing order. So A is my smallest angle, so I just double check my numbers for my sides and make sure that side A is my smallest number. And angle B is my biggest angle, so double check, make sure that side B is your biggest side. That's the easy way to check a mistake, find a mistake. Anybody questions on that one?
So you just use the method of multiplying the denominator of like C or B by both sides.
Yeah, that's
Correct.
why I just skipped steps, but yes. But it's fine. If you want to cross multiply and then divide because you're more comfortable with that, then do that. I mean, shortcuts only work if we get it right. So do what you're comfortable with. Anybody else? All right, well, let's take a look at some application problems then. I like trig because there's so many good applications. So 2 ranger stations are located on an east-west line 10 miles apart. A forest fire is located on a bearing of north 42 degrees east from the western station, which they've labeled A, and a bearing of north 15 degrees east from the eastern station that they labeled B to the nearest 10 miles, not 10, to the nearest 10 miles. How far is the fire from the western station? All right, so let's look at this diagram. They already gave us a bunch of it. All right, we don't have enough information to get started, right? So what other things can we add to this diagram that we know? Remember that this here is a north-south line and this is an east-west line. What do you know about a north-south line and an east-west line like together?
90-degree angle.
90-degree angle, right? So if I know that this right here is a right angle, and we know that part of that angle is 42 degrees, what does that do to the other part of the angle?
Forces it to be the complementary.
Perfect. Forces it to be the complement, which is what, 48 degrees? And then we've got the same thing happening here. I know that this is a 90-degree angle, and then I got that little sliver of 15 on the other side, so we can conclude that this whole angle here is 105. All right, I feel like I need to do a breakout triangle. There's a lot going on that diagram. This is side B. This is 105. This is 48 degrees. So these got 2 angles. One's 48, the other is 105. Then that tells me what this third angle here is. Oh, and we know they all have to add up to be 180 degrees. So that forces this to be 27 degrees. And we have this distance on the bottom of 110. The reason I had to get that 27 degrees is because in order for law of sines to work, we have to have a known pair. And at that point, I didn't have a known pair, but now I do. So we can get started. Those two pair up. We're looking to find angle B, I'm sorry, side B. So what angle pairs up with that one? The 105. So we're going to use these 4 things to write our proportion, and then we can solve. Questions at all on the setup before we get started on the solve? 110 miles over sine of 27 degrees is going to be equal to b over sine of 105 degrees. We can cross multiply and divide, or you can just multiply both sides by sine of 105. We get b to be 110 sine of 105 degrees divided by sine of 27 degrees. And we're going to pop it in our calculator and then round to the nearest 10 miles. Anybody get an answer? Anybody? Answer? Round it to the nearest 10? You know, I was just talking with some teachers last night, the remote teaching. You guys got to talk. It makes it so boring for us. All right, B equals 230 miles. There we go. Did anyone who actually put it in their calculator get anything different and need to talk about it?
I got 234.
But then we're rounding to the nearest 10.
Oh, sorry.
So since 4 is less, we're going to
Yeah.
round down. Anybody else? All right, we're going to do one more. Engineer wishes to measure the distance across a river. He determines that angle C is 112.90 degrees, angle A is 31.10 degrees, and side B is 347.6 feet. Find the distance A. We'll round our answer to the nearest hundredth. Well, in order to use law of sines, we have to have a known pair. Do we have a known pair?
Not yet, but we can do a small amount of work and get one.
Okay, so what's that small amount of work to get one?
Adding the two angles, subtracting them from 180.
That's right. We can get our angle B by doing just what Neil told us to do. That's 36 degrees. And then now we have a known pair, angle B and side B, that allows us to use law of sines. 347.6 over sine of 36 is equal to our unknown side A over sine of our angle A. And then we solve for A. We get A to be a 347.6 sine of 31.10 over sine of 36. And we'll pop it into our calculator and we're rounding to the nearest hundredth. Well, since angle A is smaller than angle B, I'm anticipating a distance less than 347.6. And our calculator does give us something less, 305.46 feet. Questions at all on law of sines? Oh, there's one more application. Oh, that's the toughest one though. All right, never mind. I'll save that for Tuesday. I know we're a couple questions behind, but no big deal. So I'm betting that you guys have a Dropbox quiz due on Monday night and a set of homework due on Monday night for section 6.2 and 6.3. If you have any questions on any of that material, please let me know. Otherwise, have a great weekend and I will see you on Tuesday. Like I said, I'll be wrapping up the rest of the tests today and hopefully all the rest of my grading tomorrow. Have a good day.
So homework on Monday and take home